Hey everybody, and welcome to Geology 112, Dinosaurs in the Age of Reptiles. This is our first lab. The way that we're going to be doing lab is I will provide this introduction to walk you through the reading that you need to do on Canvas for the lab. And then when you get to a certain point, you'll be going to your regularly scheduled lab times to looking at a couple of the samples and specimens that we have out to complete this lab exercise. And then you'll take good notes and do some of the work there and then do the rest of the work at home. Just a reminder that each lab unit is open for 2 weeks. So you have 2 weeks to complete the exercises within the unit. So for example, this is lab unit 1. This will run through week 1 and week 2 of the semester. And during this time, we'll be doing exercises 1, 2, and 3. So you definitely want to come to at least a portion of your regularly scheduled lab time. I'll be letting people in, maybe 6 or 7 people at a time, to collect some data, and then we'll cycle through just to kind of keep the distancing up. And if you need to get back into the lab during something outside of your regularly scheduled lab time, please feel free to reach out and we can definitely set something up to accommodate that. So what I'm going to do here is just kind of walk you through our review of rocks and minerals for our first lab unit. So again, this is exercises 1, 2, and 3. So we're going to start out with exercise 1, and this is all about minerals, which really are the building blocks of rocks. So a lot of times, students will walk into the lab and they'll see mineral samples laid out and they think, oh, we're doing rock identification. Not exactly. You're actually looking at minerals. So think of it this way. Minerals are to rocks what building materials are to a house. So if you were to go to Lowe's or Home Depot because you wanted to build a house, you wouldn't buy a house there. You'd buy lumber and concrete and nails and screws and drywall and wire. And minerals are the same way with rocks. Rocks are composed of minerals, different kinds of minerals and different sizes of mineral crystals. So what exactly is a mineral? Well, a proper definition of a substance to be a mineral, it has to meet a certain couple of criteria. First, the mineral has to satisfy all 4 of these criteria. First of all, naturally occurring substance. It has to exist in nature. Now, we can replicate many of these crystal structures in a laboratory setting, and we can study those, and that's great, but that doesn't count as a true mineral. It has to be naturally occurring. It also has to be inorganic. And what I mean by inorganic is it can't come from a living source. So I'll use the example of diamond in this case. Diamond is a mineral. Its chemical formula is carbon. It's pure carbon. And as you may have learned back in grade school, one way of hypothetically making a diamond is taking coal, which is also carbonized plant material, and compressing it down deep in the earth. Now that's an oversimplification of this process, but ultimately it's the same thing. If you take dead plant material and you stack it up and boil it down to carbon, you get coal. And we'd still call coal kind of a fossil because it's made of an organic source. But if you take that carbon and you break it down to its individual molecules and restructure it under a high pressure system deep in the earth, that's an inorganic substance. The organic origin is gone. So it has to be inorganic. It also has to have an internal structure that is ordered. This is actually a really fancy way of saying it has to have a crystalline lattice, a crystal structure. So if you look at salt, for example, the salt that might be in your salt shakers, that's the mineral halite. And if you look at it with a microscope, you'll see that the salt grains are tiny little cubes. And that's a reflection of the chemical formula and the way that the molecules are actually bonded together to produce a cubic internal ordered structure. So if you take a mineral and you melt it down into a liquid, it's no longer a mineral because it doesn't have that ordered internal structure. And it has to have a fixed or uniformly variable chemical composition. For example, halite, table salt, has the chemical formula of NaCl, or sodium chloride. If it's not NaCl, it's not sodium chloride unless it's not halite. If you take the sodium out and you add hydrogen, where it's HCl, that's definitely not salt. That's hydrochloric acid. That's dangerous. So it has to have a naturally occurring substance, inorganic, ordered atomic arrangement or internal structure, and a fixed chemical composition. Those are the 4 criteria that identifies something as a mineral. You could also put it into a long sentence. A mineral is a naturally occurring inorganic substance with an orderly internal structure and a fixed chemical composition. All 4 components are there, and that's how we define minerals. But what about how we identify different kinds of minerals? This is where physical properties come in. And one of the things you'll be doing in lab is kind of playing around with some of these properties or collecting some information and then going back to your lab printout from Canvas and identifying some of these minerals. So luster, color, streak, hardness, fracture cleavage, and miscellaneous properties. This is not an exhaustive list by any means. These are just some of the more commonly used physical properties to identify minerals. I want you to think about this the same way you would maybe going to the doctor. If you go to the doctor and say, I'm not feeling well, you'll list off some symptoms, and the doctor will then take those symptoms and run some tests and tell you what is the most likely ailment that you have. Similarly, we're taking minerals and we are identifying their properties or symptoms to diagnose what kind of mineral we're looking at. So you don't want to use any one of these properties by themselves. You want to use as many as possible. Just like if you went to the doctor and said, oh, I've got, a runny nose, you don't want them to say something like cancer, right? That's very unlikely. You want them to go through a differential diagnosis, and that's what we're going to do here. We're going to look at as many characteristics or symptoms, so to speak, of our minerals as we can. So first up is luster. Luster is simply the way in which a mineral reflects light. And there's a number of different types of descriptors for this. You can have metallic minerals, non-metallic minerals, and even among non-metallic, you can have earthy, dull, pearlescent, iridescent, waxy, vitreous. We're going to keep things pretty simple for this course, and we're just going to focus on whether the mineral is metallic or non-metallic. Color is, ironically, probably the first property that we identify when we're looking at a mineral, like, oh, this one's purple, or this one's pink, or this one's yellow, but it's probably the most useless. There are some characteristics of color that can be important. For example, light colored and dark colored minerals typically tell you something about bulk chemistry. So a light colored mineral is probably going to have more silica and oxygen in it. A dark colored mineral is going to have more iron and magnesium. So for the purposes of this course, we're going to be focusing on color being light or dark. But I bring up color because it's very easy to fall into that trap where you're trying to memorize minerals based on their color. And that's a bad thing to do, because quartz, for example, can be a variety of colors. In fact, of the 5 minerals you're looking at on this slide, those are all quartz. But notice how many different colors they can be. So you want to go beyond color, but notice they're all light colored. You go beyond color and look at other physical properties such as crystal form, fracture, and so on. So it's important to use, just don't rely on it exclusively. Streak. Streak is actually an important characteristic when comparing to something like bulk color. So streak is what happens when you take a mineral and you grind it against a small piece of unglazed porcelain tile and it leaves a mark, or it doesn't. Whether it does or doesn't, you want to write down what you see or take a note of what you see. Some minerals have a streak that's different in color than the hand sample color. Sometimes it's the same. For example, the metallic mineral hematite, which is dark gray to, again, kind of a metallic luster, when rubbed against a streak plate will leave a reddish brown streak. What you're really doing with streak is taking a small amount of the mineral and you're pulverizing it into a powder. This increases the surface area and it oxidizes. So essentially you're seeing what this mineral looks like when it is exposed to oxygen. Does it rust or not? What kind of streak color does it leave compared to the hand sample? Sometimes the mineral doesn't leave a streak. In fact, the mineral is harder in density than the streak plate and it scratches the streak plate, and that's important to note as well. And that brings us to hardness. We use something called the Mohs hardness scale, which is a relative scale for hardness of minerals. So we list 10 common minerals from talc to diamond, softest to hardest respectively. Now, this is obviously not an exhaustive list of minerals, but these are some common and well-known minerals that we can use. So talc is a 1. It's very soft. Well, how soft? Well, if we look at some common objects, like your fingernail has a hardness of about 2.5. So your fingernail is harder than talc, so you should be able to scratch talc. It should also be able to scratch gypsum, which is a 2. But calcite is a 3, so your fingernail will probably not scratch calcite very easily. A steel knife or a steel nail or a knife blade, for example, is a 6 to a 6.5. So quartz should be able to scratch that, but it shouldn't scratch quartz. Notice glass is right there in the middle at about a 5.5, and that's what we're going to use with our hardness for these mineral samples you'll be looking at. Pretty much you're going to have a piece of glass and you can scratch the mineral on it. If it scratches it, then that means the mineral is harder than glass, meaning it's harder than 5.5. If it doesn't scratch glass, it's softer than 5.5. So that's what we'll be doing with hardness, is harder or softer than a piece of glass that will be provided to you in lab. Next comes fracture and cleavage, and this property is probably the single hardest to kind of visualize, because it works fine when you're looking at a ball model, such as you see to the left, but when looking at actual mineral samples, they can sometimes demonstrate this property in not so easy to identify ways. All minerals are, a collection of chemicals that are bonded together by different kinds of chemical bonds. Some chemical bonds are weaker than others. So just as I said, halite, its crystal structure is a reflection of its chemical structure. You can go into a salt mine and see gigantic cubes of halite, and if you hit them with a hammer, they break into smaller cubes, and they'll break down to those smaller cubes until they get to the molecular level. This is a cleavage that is a reflection of the chemical composition. Okay, so for example, halite forms cubes and it breaks along cubic planes. Thus, it has 6 sides like a cube, but think about how many of those sides are parallel. You have a top and a bottom that are parallel, a front and a back that are parallel, and 2 sides that are parallel. So think about any kind of dice. It's got 6 sides, but 3 sets of parallel surfaces. Those are analogous to cleavage planes. So for example, halite, such as you see in the image there on the right, halite has cubic cleavage, so it has 3 planes at 90 degrees to each other, 3 planes of cleavage. Now, not every mineral has cleavage. Some things don't. Things like quartz, for example, forms really nice crystal faces, but if you break them, they break into jagged, sharp pieces. So this has fracture and not cleavage. So you want to look at how many cleavage planes the mineral has, which, remember, look for smooth parallel surfaces on the mineral. So here's a couple of examples. You can have things like biotite and muscovite, which are micas that have basal cleavage, or one plane. These peel off like sheets. You can have prismatic or non-prismatic. This would be whether they're at right angles or not. Cubic, which would be like halite and galena, which form nice little cubes. You have things like calcite, which form rhombohedral cleavage planes. So it looks like a cube that's been squished. Fluorite, for example, will have 4 cleavage planes, meaning 8 sides, so it's like a double pyramid. And then some things like sphalerite have 12 faces and 6 cleavage planes. They form dodecahedrons. Don't worry, we won't be looking at anything that complicated. This is one, though, that can be a little bit tricky. So if you're starting to struggle with cleavage and fracture, don't hesitate. Please reach out and ask for help, and we can get you on the right track right away. And then there's some other kinds of miscellaneous properties. Things like calcite, for example, or dolomite will react mildly when hydrochloric acid is dripped on them. So in lab, you'll have these little vials of very dilute hydrochloric acid. It's about as strong as lemon juice, so if it gets on your hand, it won't hurt you, but make sure you wipe it off. A little single drop will cause it to bubble and effervesce, similar to if you mix vinegar and baking soda. Magnetite is magnetic. Sulfur smells like rotten eggs and is flammable. So all of these different minerals have different properties, and these can be helpful in kind of steering you along a way when you're trying to diagnose what these minerals are. So that kind of concludes the mineral portion for exercise 1. What you're going to be doing is going through the exercise on Canvas, and then you'll be prompted at one point to go into the lab to actually look at some mineral samples. We're also going to be covering igneous rocks here in exercise 2. Now, igneous rocks are composed of minerals, specifically different crystals. Now, the mineral samples you'll see in lab are nice hand samples. When you see them in an igneous rock, they're a little bit harder to identify because they're very, very small. But igneous rocks form when we have a molten body of rock, such as a laccolith or a magma chamber deep underground. And if that cools in place, where we have magma cooling in place, you can get an igneous rock. Or if it erupts at the surface as lava and cools, you can get an igneous rock. So we look at our igneous rocks based on their composition and their texture. Composition being what kind of minerals are in them, and the texture is how big are those crystals in that rock, because that tells us something about the temperature at which the rock cooled. Magma deep in the earth, slowly cooling, will produce larger crystals because there's more time and insulation for those crystals to grow. When lava erupts at the surface and cools more rapidly, there's no time for those crystals to get large, so you end up with a very, very fine-grained texture. Now, different minerals will form and cool and crystallize at different times. Notice quartz will actually start crystallizing around 600 degrees. Meanwhile, olivine doesn't crystallize until around 1200 degrees. So different types of minerals form at different temperatures, and we call this Bowen's reaction series. When you get into the pyroxenes and the amphiboles, there's a bunch of different minerals that fall into those categories. The feldspars as well, like plagioclase. So if you have an igneous rock that's mostly orthoclase feldspar, muscovite, and quartz, that's going to have formed between around 600 and 800 degrees. If you have an igneous rock that's mostly calcium-rich plagioclase, pyroxene, and olivine, it formed at a much, much higher temperature. So our fine-grained igneous rocks, we call that texture aphanitic. And aphanitic textures form extrusively. They form at or near the surface very, very quickly. There's very, very small grains here. They're less than a millimeter. You need a hand lens or a microscope to see them. Now, you can have the same composition, the same minerals, but that rock formed intrusively deep in the ground very, very slowly in a magma chamber where you now have larger examples of those same minerals. We call this larger texture phaneritic. And this is where the grains are larger than a millimeter. So you can see them with the naked eye, but they can still be very, very tiny. So you can have two rocks that have the same chemical composition that formed at the same temperature, but they cooled in different places. If one cooled rapidly, you get an aphanitic version of that rock. If it cooled phaneritically or intrusively, slowly, you get the phaneritic version of that rock. You can also get extremes where the rock cools very, very slowly in the ground, the magma cools very slowly, and you get gigantic 2 to 3 centimeter wide crystals. We call this a pegmatitic texture. And this is where you get big minerals that are easy to identify in those igneous rocks. We also have a really strange situation where we have both textures present in the same rock, and we call this porphyritic. Now, how does this form? Well, let's think about it. We know that we get large crystals, phaneritic crystals, from slow cooling, and we get fine-grained crystals, aphanitic crystals, from rapid cooling. So what if we had a magma chamber deep underground and it's starting to cool off, and we're forming larger phaneritic crystals? And then that entire blob of magma gets upthrust towards the surface, and it cools rapidly, producing a fine-grained matrix surrounding our larger crystals. That is going to be a two-stage cooling effect, where you have intrusive and extrusive igneous rocks at the same time. And we call this specific texture porphyritic. It's more common with our phaneritic textures, but we can get it with aphanitic as well, where you can have a bulk of the rock is aphanitic with some fine-grained stuff. Usually, though, it's the other way around. It's mostly fine-grained with a couple of large, what we call phenocrysts. Regardless, we call both cases a porphyritic texture. So, if we compare this with mineral composition, kind of going along the top, and textures going down the side, we can see that we have different groups of igneous rocks based on their composition. So for example, felsic rocks. Felsic rocks are greater than 10% quartz. They have about over 50% feldspar, whether it's orthoclase or plagioclase feldspar, and a little bit under 15% of the darker minerals like muscovite, biotite, and hornblende. Now, if you have a coarse-grained phaneritic felsic rock, we call it a granite. If you have an aphanitic fine-grained felsic rock, we call it a rhyolite. If it's a mixture, we usually call it a rhyolite porphyry. You go over to the next stage, which is the intermediate mineral composition, which has a little bit less quartz, a lot of plagioclase, a little bit less orthoclase, and it has kind of a lower amount, but still respectable, of our hornblendes. So this is going to be an intermediate igneous rock, and these really do look like a black and white specked rock. It looks like salt and pepper. We call the phaneritic version of this diorite. We call the aphanitic extrusive version of this andesite, as in erupted from the Andes mountains. And if it's a little bit of both, we can sometimes call it an andesitic porphyry. And then we get to our mafics. Mafics are magnesium and iron rich rocks. These are dark, heavy rocks. They have a lot of calcium and plagioclase, a lot of augite and olivine, virtually no quartz, and no orthoclase, no micas. So this is going to look like a big black rock. But if you can see crystals, it's phaneritic, and we call it gabbro. And if it just looks like a dull, flat, black rock, we call it a basalt. Now there's some other textures that can pop up in here too. When a rock is cooling, there can be a lot of gas escaping, and that produces holes, kind of like Swiss cheese, and we call those vesicles. So you can have vesicular basalt or vesicular andesite in some cases. And then we have these rare types of rocks that we see called ultramafics, which are pretty much just pure olivine and pyroxene, and we call that a peridotite. You don't have to worry about those because we won't be seeing any of those this week. But felsic, intermediate, and mafic, there's 6 of these different rocks that you should be able to identify. 2 felsics, 2 intermediates, and 2 mafics, the phaneritic and the aphanitic versions. Okay. And this, another way of looking at this, same type of thing, where notice if we look from the felsics and we go down, you can see the relative percents of the different minerals, and we have our rhyolites and our granites. Intermediates, you can see we have very little quartz there, but much more plagioclase, hornblende, and augite or pyroxene, and we have our andesite and diorite. And then our mafics are dark, heavy minerals, basalts, and gabbros. Now, what about our metamorphic rocks? Well, a metamorphic rock is a rock that starts out as one kind of rock, but it's been heated and squeezed almost to the point of melting, and it transforms. So even in this diagram, you have your original rocks, which we call parent rocks. That could be quartz sandstone, shale, limestone, basalt, granite. And then as you start increasing the temperature and pressure, they change. A basalt might change to a chlorite schist, to a serpentinite. And then once you get melted, it starts all over as an igneous rock. So just as we did with our igneous rocks with our texture composition comparisons, we do the same thing with metamorphic rocks. Okay, so this is directed pressure or stress where we're uplifting rocks or we're squeezing and stretching them, and it upsets the original bedding forms of these rocks, and they become completely transformed with heat and pressure. If these rocks have any clays or micas in them, clay minerals or mica minerals in them, they will start forming layers. We call these sheet-like layers foliations. Now, if the rock doesn't, the parent rock doesn't have any quartz, doesn't have any clays or doesn't have any micas, it's not going to get that foliation. So we call them non-foliated. So here are some foliated metamorphic rocks. Slate is the lowest grade of our foliated rocks. This is what happens when you take shale, which is a mudstone, and you heat it and squeeze it, and you get slate. The differences between the two, you can feel the difference. Their density is different. But notice, looking at slate, it's got very thin cleavage planes. You can bust them off into sheets. If you take slate and you increase the temperature and the pressure a little bit, some of the clays that are in that slate are going to start transforming into very tiny microscopic micas. And so you end up with a rock called phyllite, which still has the layering, but it's got a shine to it. It almost has a silky or satin-like sheen to it. That's a low medium grade metamorphism. Now, if you take phyllite and you increase the temperature and the pressure to a high medium grade, you get schist. Schist is also foliated, but in this case, those microscopic micas in our phyllite have welded together to produce larger flakes of mica. And so schists have a very glittery, scaly, flaky texture to them. And then if you take schist and you increase that temperature even more, you're at the threshold of melting that rock. You get a gneiss, G-N-E-I-S-S, gneiss. And this has a banded appearance with dark and light layers alternating. And what's happening in this case is the rock is so heated, the minerals start moving through to band together. Now, it's not fully melted yet, but if you increased it much more after this, it would melt and we'd start all over with an igneous rock. So we use gneiss as our highest grade of metamorphism. Our non-foliated rocks are a little different because these don't have any clay or mica to form layers, so they're just kind of massive, which means these are a little bit harder to identify sometimes. Quartzite, for example, is made of pure quartz. We start out with a quartz sandstone and we heat it and squeeze it until the grains weld together. So this is identifiable by having some of the same properties as a quartz crystal, such as its hardness. Marble, on the other hand, looks a lot like quartzite, but it's made from limestone, a sedimentary rock which is dominantly calcite. So if calcite has a hardness of 3 and it reacts with hydrochloric acid, so will marble. So if you're looking at quartzite and marble and trying to differentiate them, that's one of the best ways to do it, is see which one's harder than the other and which one reacts with acid and which one doesn't. Another non-foliated metamorphic rock is serpentinite. This is a very high-grade non-foliated rock, and it's usually associated with very, very high degrees of metamorphism. So when you're looking at your metamorphic rocks, you want to use a table kind of like the one that you have on Canvas, where you have your non-foliated and your foliated rocks, and you want to look at the properties of these rocks and compare it to what you're seeing in the hand sample. And then we get to exercise 3 for Unit 1, and this deals with sediments and sedimentary rocks. So this is what happens when you have unconsolidated fragments of pre-existing rocks or minerals. So we can start out with anything. We can start out with pieces of organisms remains like fossils, or we can have sedimentary rocks, igneous rocks, or metamorphic rocks, or even just minerals. And they break down. They weather and erode into pieces. If the pieces are fragments, we call them clasts, C-L-A-S-T, or if they get dissolved into water, we call it a chemical sediment. When we're dealing with clastic sediments, we're characterizing them based on shape, size, and composition. Again, we're talking about sediments, not necessarily the rocks yet. These are the things making up our sedimentary rocks, our recycled pieces of pre-existing rocks and minerals. We do use something called the Wentworth scale when describing the size of the grains, not the rock sample, but the grains making it up. So we call something mud if it's a silt or clay size. This is 4 thousandths of a millimeter or smaller. Sand can be 62 thousandths all the way up to a millimeter. Then we go to pebbles, cobbles, and boulders, which get larger. So our mud, sands, and gravels. And we can use these to identify what kind of sediments sizes we have within a rock. And the reason we pay attention to size of the grain is it tells us something about the energy that moved that grain. So if you've ever been whitewater rafting or seen anybody go whitewater rafting, there's not a lot of muds and clays and sands in that river channel because the velocity is so high, it shoves it all downstream. So what you're left with are these giant boulders and cobbles and pebbles that aren't able to be moved by the velocity of that water. Similarly, if you go into the middle of a quiet lake, there's a lot of mud because the velocity is very low, thus muds can fall out of suspension and land at the bottom. So we pay attention to the size of the grains because it tells us about what kind of environment it was. So here's a diagram from your lab that shows the relationship between particle size and how they move. So notice that when we get to something very, very large, like our pebbles and cobbles and boulders, you need a very high velocity of flow to actually pick those things up and move them. And if it falls below that velocity, then they settle out. And for the most part, the smaller you go, the lower the velocity is needed to move it. The exception here are very, very fine clays, and that's because clays are sticky. Think about when you get mud on your shoe, right? It's very, very sticky, so you need a high velocity to break those clays apart, and then they actually start to behave like other particles. We also pay attention to composition because some minerals are more stable than others. So quartz, for example, is a very, very stable mineral. So we have a lot of sedimentary rocks with quartz in them. However, olivine, pyroxenes, and some of our plagioclase feldspars are not nearly as stable at the surface. So they tend to weather and break down. And this produces a bit of a bias with what kind of rocks or what kind of minerals make up a majority of our sedimentary rocks. Quartz, muscovites, potassium feldspars are very, very abundant, and some amphiboles, but most of the time quartz and muscovite and potassium feldspar make up a significant portion of our clastic sedimentary rocks. We also describe the grains in terms of their shape. Because if you start out with a granite and you break it into sedimentary pieces, those pieces are going to be angular and jagged. So how do we end up with rounded fragments? Well, that tells us something about how that grain maybe tumbled downstream for thousands of years and eventually became rounded. So we'll look at a sedimentary rock, a clastic sedimentary rock, and we'll describe the size of the grains, the composition of the grains, and the shape of the grains. And that tells us something about the history of those sediments and the history of the environment that they represent. Because just like our igneous rocks told us about where the rock cooled at or near the surface or in the ground, metamorphic rocks tell us about how rocks have been deformed from heating and squeezing. Sedimentary rocks, which we'll be dealing with the most in this class, tell us about ancient environments. So when we talk about wanting to learn about dinosaurs and how they lived and what kind of world they lived in, we have to look at sedimentary rocks. So we put all this information together and we describe the sorting of a sedimentary rock. So on the far left of figure 5, you can see that all of these grains in this dish are about the same size. That'd be well sorted. And if you look at the far right, we have large, we have small, angular, rounded. That's poorly sorted. The more well sorting, the more consistent that environment is. So river channels, for example, are very, very stable. They usually have a relatively stable amount of flow. Or if you go to the beach, you see sand getting washed around. That's because the wave energy is pretty consistent. Now, when a big storm comes in with a very high velocity, it mixes everything up. So if you have a well-sorted rock, that tells you it came from an environment that was relatively stable. And if it's poorly sorted, it tells you it was relatively unstable. So if you were to look at a bunch of sedimentary rocks, how would you determine what they are? Well, first you want to look at the texture. Is this rock clastic or is it chemical? Clastic means you're going to see pieces of visible rock fragments. It's going to have a sandy or a gritty texture. And then you want to go through and describe the size and the shape of the grains and their composition, and then use the tables in the lab to help you identify what kind of minerals you're looking at and what kind of rock it is. Now, if you look at that rock and you cannot see individual grains and that rock reacts with acid, there's a very good chance, not entirely, but a very good chance that it's a chemical rock, meaning that these are mineral grains that dissolved in water and were then transported somewhere and then regrew. So imagine if you were to take a glass of water and you put salt into it, the salt would dissolve. If you boiled the water off, the salt would grow back. That's how chemical precipitation happens, and that's how we get what we call chemical sedimentary rocks, or biochemical if it's organic in origin, like shell fragments, like a fossiliferous limestone. So you want to look through the samples and identify what's chemical, what's clastic, and then identify them accordingly from there. So for Lab Unit 1, we have 3 assignments, exercises 1 through 3. The first part of these you will find under lab exercises 1 through 3 in Canvas, and it's going through the reading that I've provided on Canvas and answering some questions that go with it. There's then a portion where you'll come into the lab to actually look at some samples. So you want to go to your regular scheduled lab meeting, time and place, look at the mineral and rock samples as instructed on Canvas. You want to take really good notes and observations. Feel free to take photos. I've also included 3D interactive files on Canvas so you can rotate these and look at them at home. And you want to fill in the lab manual or what's online or fill in some details and then transcribe those results into the spaces provided in Canvas for grading. Please make sure that you're wearing masks and gloves at all times in the lab. And I'll be letting people into the lab over the 2 weeks, maybe 6 or 7 people at a time as needed to make sure we can keep everything clean and distanced and we can still go through everything. If you have any questions about Lab Unit 1, please feel free to email me or chat with me when I see you in lab. So good luck, and please let me know if you have any questions.